Okay, so so we looked at double sideband last time, and mathematically it's pretty simple. It's actually simpler at the transmitter than standard AM radio, but we didn't talk about the receiver. Okay, so, and there are a couple of different kinds of receivers that can be used. We'll talk about the Costas receiver. The receiver is a lot more complicated than standard AM radio, where you can just essentially use a diode and a capacitor, an envelope detector. You can't do that with double sideband. Okay. So the double sideband signal is AC MT cosine of 2 pi FC of t. And then the double sideband receiver we had as a block diagram this, C prime of t is equal to AC prime cosine of 2 pi FC of t. And if this is true, you know, we can generate this signal at the receiver that has the same carrier frequency, FC, the same phase as at the transmitter. Okay. And then mixing it again, what we get is we get a component at DC back at baseband, and then we get another component at 2FC. So using a low pass filter, we can recover 1/2 AC prime MT. Okay. So that's the math. That's relatively simple. And I think in your project that's due Friday on the double sideband receiver, since I know the frequency and it's, you know, mathematical generation for the double sideband receiver, it essentially does this, if I recall, essentially a product like that. Because I've got the expression, because I generated the double sideband signal, I know exactly what frequency and phase were used, so I, you know, can generate that at the receiver exactly. But in the real world, as a practical example, again, we know the carrier frequency, but and you're talking in the megahertz here. You know, if you're off a few tens of hertz, you're going to have some noticeable distortion. We kind of saw that last time with that example. And if there's a phase shift, may or may not be bad. If the phase shift is 90 degrees, though, we get nothing out. So somehow, you know, the tricky part of the receiver is actually generating, you know, at the receiver, a replica of the carrier. So how to generate that? Well, so that there's two methods that are primarily used. One is we can transmit the carrier. Now, usually with double sideband, we don't transmit as much carrier as you do in AM radio. Remember, in AM radio, there's a large amplitude carrier, a lot of power, so we can do envelope detection. Here with double sideband, it would be a much smaller amplitude carrier. And then at the receiver, you know, we would have, you know, perhaps a bandpass filter. We could use a device called a phase lock loop that we'll look at later to actually pull out that sinusoid and then feed it back in and mix it in here. Okay, so that's one technique. And we'll talk about that phase lock loop later. But then recover at the receiver. Recover the carrier at the receiver, okay? But again, can't use envelope detection. You could actually use this same technique for standard AM radio. The carrier is already there, so that this receiver would work for standard AM radio as well. But and this is typically more expensive. It is more expensive than just a simple diode detector. And then the other technique that we'll use is a receiver known as the Costas receiver. This is kind of a complicated diagram. Okay. Most of the complication, though, comes in generating so this part is, exactly the same. Y of t is 1/2 AC. And then now I'm going to allow for, remember when we had a phase mismatch between our carrier replica and our carrier, that appeared here. And when this is 90 degrees, we get nothing out. So this is the more general expression. So this is our S of t. And then I'm going to have a bunch more stuff here that's all now just used to generate that replica of the carrier. Okay. So what we do is we use what's known as a voltage-controlled oscillator. Voltage-controlled oscillator. And this thing produces a sinusoidal output, okay. But we can vary the frequency of the output in proportion to a DC level here, okay. So the free running oscillation frequency is going to be close to our carrier, around FC. And then, but we can vary that, increase that, above or below whatever FC is, using this DC signal here. This whole thing is going to use negative feedback to actually vary this signal, to vary the frequency so that the frequency matches that used at the transmitter. Okay. So this is kind of our first example. A phase lock loop also uses negative feedback to ensure that match. So, but the output of this is essentially our AC prime, ideally cosine 2 pi FC of t. Okay. But until we achieve that match, and it'll match both in frequency and phase, until we achieve that match, there can be a phase shift. The other thing that we do is actually shift that carrier by 90 degrees to generate the corresponding sine wave. It's 90 degrees out of phase with the cosine. If you shift the cosine 90 degrees to the right, a negative phase shift, you get a sine wave. This then is multiplied by our carrier and low pass filtered. So this would be, this is an I, I'll put uppercase here. This is called the Q channel and the I channel, the in phase and quadrature channels. YQ of t then would be 1/2 AC sine phi of MT. Okay. And again, math here is pretty simple. We did it with the cosine last lecture. You can do it with the sine. Again, you'll get a component at DC, which after your low pass filtering is this. You'll get another component at 2FC, which your low pass filter removes. We actually feed both of these into what's known as a phase discriminator. Discriminator. And then this produces that error signal that drives our voltage controlled oscillator. So part part of this phase discriminator actually consists of an integrator, but it tries to, based on these two inputs, it tries to produce an error signal here. We'll look at it in a little bit more detail, what it does. That changes the frequency of our oscillator so that we have an exact match between our carrier frequency and our replica that's produced at the receiver. So the phase discriminator looks like this. Discriminator. So we have our two inputs coming into our multiplier, our yi of t and our yq of t. This is all in this phase discrimination block, so it consists of a multiplier, and then we integrate that, so we call that output g of t. We integrate that with respect to time to actually produce e of t. Okay. When the angle here phi is 0 and we're exactly matched, the product of these will be equal to 0 because this is 0. Sine of phi would be 0. So the product of these would be 0, and then integrating 0 would give you 0, and that's the match condition. So this is the integral with respect to dt. Sorry, I wrote that kind of small. I'm calling this signal g of t. You're going to look at this a little bit more in one of the homework problems I assigned today, go through some of the math here. So that's all I'll mention on it. But I want to talk about quadrature carrier multiplexing. This is a really kind of clever technique for transmitting two different messages at the same carrier frequency. And it requires a much more sophisticated receiver. It's also known as quad AM or QAM, sometimes pronounced either CAM or QAM, usually CAM. But it's a way to actually transmit two messages at the same carrier frequency. And what the receiver looks like, I'll come back over here. I'm sorry, what the transmitter looks like for CAM. We have M1 of t. And it's produced using the same technique that we've used in the past for double sideband, 2 pi fc of t. Okay. Just multiply that by our message, and then normally we would transmit that. And now we're going to take that signal, phase shift it by 90 degrees, and use that phase shifted carrier, multiply by it by a second message to produce ST. So ST now consists of M1 of t AC cosine of 2 pi fc of t plus M2 of t AC sine of 2 pi fc of t. So this is the CAM transmitter. Now, I'll put up the receiver here in just a second, but you can go through this mathematically. And essentially, if you multiply this whole thing by cosine, and then low pass filter, the sine cosine product gives you 0 at DC. Okay, and then there's a component at 2FC. The cosine cosine product gives you, again, a baseband term and a 2FC term. So if you multiply this by cosine and low pass filter, you'll recover M1. Okay. You go through the math with multiplying it by a sine. Okay. Again, the cosine sine term will give you 0 and a component at 2FC. The sine sine term will give you, again, a baseband component. This time it's M2, and then a component at 2FC. So again, you low pass filter, and you recover the second message. Okay. So this could be used to actually transmit two completely unrelated messages. It could be used for stereo AM, okay, where you've got a left and right channel, like FM stereo. We haven't talked about FM, okay, but modern FM actually transmits two separate signals on the same carrier frequency so that you get FM stereo. Sounds better than mono, one signal, okay, that's all that's transmitted on AM. But there is it's not a limitation of the modulation method. We could have stereo with AM, but everyone have to go out and buy new AM stereo receivers. And again, I think one of the homework problems I'll have you actually work through the math here to show that, what the receiver, to verify the operation of the receiver. The receiver and looks like this: low pass filter, AC prime over 2 M1 of t, and all we have to do is multiply by a cosine 2 pi FC of t minus 90 So here's our received signal, low pass filter, and this will give you AC prime over 2 M2 of t. Again, I'm leaving a lot out here on how do we reproduce this replica of the carrier. You could do that with the Costas receiver. So if you take, all of this would replace this little circle here, again, to generate the signal that's a replica of the carrier. So, and get two signals in the same bandwidth as double sideband. Okay, so we're coming to the end of our AM radio techniques. This is one of the last ones we'll look at. There's actually one more. Okay. That's called vestigial sideband, which I think we look at next time. Vestigial sideband was used with traditional television broadcasting. But single sideband I've kind of alluded to in the past, that with, when we modulate our baseband signal, we get this signal that has, upper and lower sidebands that, one's the mirror image of the other. So they contain the same information. Is it possible to transmit just one of the sidebands and recover the message? And the answer is yes, all the information's there. But the receiver is much more complicated than even the double sideband receiver. The operations involved in recovering that other sideband. And you can transmit either the lower sideband or the upper sideband. Okay. So if the receiver is more complicated, why would you ever bother with single sideband over double sideband? It uses half the transmission bandwidth. Okay, so if you look at your AM radio dial, I could get twice as many channels using single sideband than double sideband, right? So, and spectrum is a limited resource. Okay, you can't just go out and arbitrarily start transmitting AM radio. The FCC will come and shut you down. Okay, so spectrum is a limited resource. You have to apply to the FCC. It's probably going to cost you a lot of money if you want to set up a new radio station. Similarly, there are bidding wars that occur as spectrum becomes available. That cell phone companies will bid on, for the FCC to have the right to the exclusive right to, some sort of gigahertz band. But we're essentially out of freely available spectrum. So they're in the process of maybe making old techniques obsolete so that we can use newer techniques better. And that's essentially why they phased out. One of the things they could have done when they introduced the new television is actually broadcast those new television signals in a different spectrum, right? So we still could have had the old broadcast technique at those frequencies and just used newer channels for the high def, but couldn't do that. We're out of essentially spectrum. So we had to use those same frequencies for high def, transmitting though incompatible signals. So had to get rid of our old TVs. I expect, it won't be too long before they do something like that with the AM radio and FM radio bands, that the older analog techniques aren't as efficient with regard to power. They're more wasteful with regard to bandwidth. So they'll probably phase those out and then reuse that spectra for, some digital radio or something like that. It's going to be several years before that happens, I'm sure. They'll phase it in. One of the big issues with AM and FM radio is that, unlike TV, everyone's got a radio in your car, right? So not everyone's going to want to pull out their car radio and install a new radio. So single sideband uses half the bandwidth of AM or double sideband. You can have either upper single sideband or lower single sideband. So let's consider upper single sideband. And your book calls that USSB. A lot of books will call it USB, not to be confused with the USB cables on your phones and computers, or LSB for the lower single sideband case. So here's our example message spectrum. And with upper single sideband, what we want to do is essentially transmit this. So, of course, with double sideband, it's modulated up to FC, and we transmit both sidebands. Now we want to get rid of the lower sideband. So this is the USSB spectrum. We can, of course, well, maybe not of course, we can create USSB using a sideband filter. Okay. So essentially, in block diagram form, I got our transmitter, we use double sideband modulation. Okay. And then use a bandpass filter to pass through our upper sideband, these frequencies, the frequencies between FC and FC plus W, to get our USSB signal. Okay. Sounds easy, but in practice, again, it's a little more difficult because the lower sideband here is adjacent to the upper sideband. So we need almost an ideal bandpass filter here, something with a very sharp transition if we're going to completely remove that lower sideband. So it requires a very good bandpass filter in order to do this. And very good bandpass filters can be quite expensive. It requires a bandpass filter that has what's known as a high Q or high quality. That typically requires a higher order filter, a lot of capacitors and inductors in the filter to create a filter that has a sharp edge, okay, that will do this effectively. Okay. Let's see if we can come up with, this is a signal that's actually kind of easier to describe in the frequency domain than it is in the time domain. What's going on here. The pictures look pretty simple. Let's look at getting the time domain expression. What we'll do is actually do the inverse transform of the spectrum here to come up with the time domain expression. So let's find USSB of T. Okay. So we'll start with the frequency domain expression. Which I'll write like this. It's 1/2 m of F minus FC, and then 1 plus the signum of F minus FC. Now 1 plus signum, that's essentially a unit step, okay, that starts at FC. And then so, this is our baseband spectra that's shifted to the right. Okay. And then this will filter out the lower sideband for me. Again, we could write that as a unit step, but writing it this way makes it actually easier to write it in terms of a signal that's known as the Hilbert Transform. Okay. Plus 1/2, and then we'll do the same thing with the negative frequency spectra. That's 1 minus sine of F plus FC. So here's the signum function or the sine function. It's equal to 1 when its argument is positive, and it's equal to -1 when its argument is negative. It essentially just finds the sine of whatever the number is. If the number is 10, signum would give you 1. If the number is -10, signum would give you -1. Okay. Now, what does 1 plus signum of F look like? Well, it just shifts the whole thing up by 1, okay? So the negative frequency portion would be at 0, the positive frequency portion would be at 2. We take 1/2 of that. We see that this is really just another way of writing the unit step. Okay. Equals U of T. And then similarly, the other term that's here, 1 minus the signum, 1 minus a -1 would give me 2, 1 minus 1 would be 0, so that's 0. And then this would be 1. So this is 1/2, 1 minus signum of F plus FC. And this is another way of just writing u of minus f. Now, this is not quite what I have here. I have this thing shifted to the right by fc, right? So again, it's just a unit, not u of t, u of f. Be this thing shifted to the right by fc, and then multiplied by my double sideband spectra. So it's going to create exactly this picture. Okay. It's the mathematical representation of this. Okay. So we can rewrite this as it's 1/2 m f minus fc plus m f plus fc. And this is why I didn't use unit steps, because I wanted that factor of 1 in there, because I recognize this. This is my double sideband modulated signal, right? So we're able to actually express single sideband in terms of a double sideband. But then I've got these other components. So plus 1/2 the signum of f minus fc times m of f minus fc minus the signum of f plus fc times m f plus fc. Okay. I think that's, yeah, that accounts for all the terms in that expression. Okay. But now we're going to define a signal related to m of t. We're going to define this m tilde f, that's minus j signum of f m of f. Okay. So this allows us to write, and we'll come back and take a look at how is this m tilde of t related to m of t, our baseband message. Okay, you can view this as a filter, this minus j signum of f as a filter. It's called a Hilbert filter or a Hilbert Transform filter. So now we have 1 mf minus fc plus mf plus fc minus 1/2j. Again, I've got this minus j that's in the definition of the filter that doesn't appear here, so I've got to get rid of the j and the minus sign. I get the Hilbert transform signal, double sideband modulated. Actually, the minus sign appears when you modulate using a sine wave. Okay. So I want to rewrite this one more time before I get to the final result. So I can write this as m of f convolved with 1/2 delta f minus fc plus delta f plus fc. Okay. That's this first term in brackets, right? Convolving m of f with delta f minus fc just translates to my baseband spectrum. Okay. The reason I do this is this is the Fourier transform of a cosine. Okay. And the convolution becomes multiplication back in the time domain. The other term I can write as m tilde f convolved with 1/2j delta f minus fc plus delta f plus fc, okay, which is a sine wave. So finally, we get our time domain expression. It's m of t cosine of 2 pi fc of t minus m tilde of t sine of 2 pi fc of t. Okay. So although we started with this frequency domain expression, I talked about actually using a sideband filter to eliminate the sideband. This is in the time domain, the equivalent time domain expression for that single sideband signal. It gives me actually another way to create an upper sideband modulated signal. I double sideband modulate M of t, and then this is essentially double sideband modulation using the sign, but double sideband modulating this M tilde of t thing, which we'll talk a little bit more about. Okay, it's related to M of t. Okay. You can go through this procedure again for the lower sideband signal. The only difference is you add instead of subtract. M tilde of t sine of 2 pi fc of t, where M tilde of t is called the Hilbert transform of M of t. Calling it the Hilbert transform is a little bit unfortunate because it's not a transform in the sense like a Fourier transform or a Laplace transform. We'll look at it here in just a second. But there is a one-to-one relationship between a signal and its Hilbert transform. So in that sense, it's like a transform. We can go from MT to M tilde T and back. Okay, actually, a double Hilbert transform recovers the original signal. So let's take a look at what M tilde T is. M tilde F is minus J signum F MF. So we can look at this actually as just running MT through a filter that has a given frequency response, right? If we want to multiply in the frequency domain, that corresponds to filtering. That's what our filter does. Or convolve with whatever the inverse transform of this minus J signum F is. So where H of F is minus J signum of F, which is minus J for frequencies greater than 0 and plus J for frequencies less than 0, where, or in terms of the magnitude and phase, doesn't affect the amplitude of the signal at all at any frequency. It's what's known as an all-pass filter. But then the phase angle, theta of F, minus J corresponds to, magnitude of minus J is 1, but minus J in the complex plane corresponds to a phase shift of minus 90 degrees for positive frequencies, and plus J is plus 90 degrees for negative frequencies. So this Hilbert transform filter is nothing more than a phase shifter. It phase shifts all positive frequencies by 90 degrees, and it phase shifts all negative frequencies by negative 90 degrees. So in our block diagram form, now to do this single sideband modulation, we take our baseband signal, run it through a Hilbert transform filter, this phase shifter, okay, which is not an easy filter to generate. I say, and then we subtract plus minus. So this is my cosine 2 pi fc of t, and this would then be my sine of 2 pi fc of t. And then so this would be my upper single sideband signal. So this would be an alternative method for generating single sideband. The other method would be double sideband modulated, and I had it up here earlier, and then bandpass filter to eliminate one of the sidebands. Again, it seems like the bandpass filter might be an easier method. Both methods are used. The bandpass filter method, again, requires a very costly filter, high quality filter implemented at radio frequencies. And it also depends on whether you're trying to do this for, again, broadcast, where all your expense in your transmitter is just at one transmitter, or if you're doing two-way communication where everyone has to have a transmitter and receiver. Again, either method can be used. Both are actually methods are used in practice. Okay. All right, that's it for today. I think we're getting close to finishing this chapter up, so I should have an exam coming up pretty soon. I don't know when it is. I think maybe actually 2 weeks.